So morning, everyone. It is currently Thursday, January 21st. We're going to be continuing on with access control today, and we'll be playing this recording on Monday night at 6 p.m. for the whatever that session one. I don't know, remember exactly what we phrased it, but if you're watching then, thanks for both people, try to, I think it really helps to stay engaged with these remote lectures if you participate in the chat. So I think that is very helpful. So when I ask questions, I think that is a good way to stay engaged and participating. So what we're talking about here is how do we model access control? So we talked about this before. So what we're going to do is we're going to introduce a little bit of mathematical notation here. So we'll have a set of subjects in our system S, and subjects are, as we talked about, things in the system that can act. So these are things that can actually do things and take actions in our access control systems. So we originally, if you recall, on Tuesday, brought up the notion of this student and professor system where students and professors could act because they could read homework files, create homework files, change ownership of homework files. And then we have a set that represents all of the objects in our system. So this is the set O that represents all of the assets or objects in our systems that can be acted upon. So can something be both in S and O? So can something be both a subject and an object? And what's an example of that? Yeah, so in our example, students, right? A student can be acted upon because we had a professor that could kick them out of the class. So a professor can act on a student, and students can also, so they're an object in that sense, and they're also subjects because they can act. Great, okay, cool. Look at that, y'all remember what we talked about in the last class. That's a step in the right direction. And then we're going to have our set R of rights. And these are, you can think of rights as rights or privilege, but basically what can the subject do to the object? So let's stop here and we'll refresh where we were. Let me bring up our old notes here. Cool. Okay, you won't be able to see it yet. I got okay, and then if I resume sharing, you should be able to see. So now, can you see the Emacs screen on the left? Yeah, cool. Okay, I was challenged to move from Notability to Emacs by one of the students, some of the students in Wednesday, or what was that? Yeah, Wednesday's viewing. So we have our same policy here, right? So students should only be able to read their own homework files. We have the access control policy, the access control rules that we've implemented here. We have two students, S1 and S2. We'll have two professors, P1 and P2. So this would be our set subjects, so things that can act in our system. We have S1, S2, we have P1 and P2. Do we have anything? So do we have, let's say, homework 1, homework 2, these are our homework files. Do those belong in S, the set S? No, and why not? Yeah, because they can't act, right? So that's great. So there's nothing that a homework file itself can do. They're not altering or changing the access control in the system. So we have homework 1, homework 2. What other objects do we have besides the homeworks? Students, yeah, so S1 and S2. Awesome. Now we need to think about the rights. So we have the rights that and rights are specifically about what a subject can do on the object. So not everything, not every right will be in here, as we'll see. But let's say CHOWN, one right could be that they can change the ownership of that file. Maybe another right could be a read is a clear right that we have. Edit, yeah, edit, or let's say read, write. Oh shoot, I am using this. I want to save this notes. This bar is right in the middle of where I want to be looking at. That is not what I want. There we go. Okay. Yeah, so we have create, but create is actually kind of a special thing right now because we don't really have a way to create new objects yet. So let's kind of just ignore that for now, but we could think of maybe create being not necessarily a write, but maybe some kind of actions, right? So that would be maybe an action that they could take, because it's not that we have a create on a specific thing. Own. Yeah, okay, so we have owns, and then we have some kind of, so these would be essentially our actions, creates. So we could have something like creates, change ownership, right? So these are actions that we can take that may be of our system that will either succeed or fail based on the rules here. So what we can do is think about, and what we're going to do is model the current access control rules of the system. Oh, it's frozen. Okay, let's stop sharing. How about now? Good. Nope, not good. Still can't see it. This is worse. Okay. Second time the charm?
It's still not showing.
Maybe it's just taking a bit to load your screen or something.
That's weird. I mean, I don't think I've ever seen this Zoom problem before. Okay. Let's do share screen. Maybe optimize for video clip. We'll do something different.
It worked.
Better? Okay.
We can see stuff now, yeah.
Yay, stuff. Stuff is always good. Okay. Cool. So basically we updated these sets. So in our small little example, we have our subjects, we have our objects, we have our rights, owns, read, and write. And oh, action. Yeah, we have another action called kick. All right, let's try just sharing. All right, I will try just sharing the one application, although I kind of want you to be able to see both, but that's all right for now. How about there? Is that better? No?
Yeah, I can see the text.
Much better? Okay. Cool. That is bizarre and frustrating. Okay, so maybe it's okay. Anyways, we'll figure that out. Okay, so now we need to be able to, and we want to be able to understand. So if I have a given system, what is the current state of the system? So let's say I went through some things where S1 creates a homework file, and then so we went through this scenario, right? So now what we want to be able to do is we want to be able to understand about the system exactly what the what are all of the rights that all of the subjects has on all of the objects. And so let's think about how that would look like. And actually one of the nice things we'll do here is we'll create a table. So we'll think about, okay. let's add something like, so we have S1, S2, homework 2, S1, S2. Okay, and then I will have S1, S2. Yeah, okay. So can everybody see this table? It's in purple. I don't know if that's a great color. I can also make the screen bigger if that's a problem. Okay, cool. So what we're going to do is we're essentially going to make a table. So we'll have as our rows all of our subjects. And now we want to know for every subject in the system, what rights does it have for every object? So let's say we went through S1 creates homework file H1. So you can think of S1 dot, well, when we're just kind of making this, this thing dot creates, let's say homework 1. Right, so we have some action. So S1 takes an action on the system, creates a homework file H1. So what does that mean that S1 has? What rights does S1 have over homework 1? Owns. Any other rights? Yeah, they can also read and write, right? So this would be we'll think of it as a set. So we have a set that is, they own that file, can read that file and write that file. And let's say S2 creates a homework file, homework 2. So does S1 have any rights on homework 2? Nope. Does S1 have any rights on S1? Can S1 act upon S1 at all? No. Can S1 have any rights on S2? No, right? Students can't act on other students. Oh, and I see that I'm missing a row here. P1, P2. Okay, great. So S2 now. So does S2 have any rights on homework file 1? Nope. So it'll be the empty set. What about homework file 2? Right, so it'll have all of them again. Exactly. Does S2 have any rights on S1? Nope, because they're students. Great. And I'm missing a, let's call can kick. Okay. Now, Professor 1, does Professor 1 have any access to homework 1? Yeah, possibly, right? We actually don't know. It's not specified in our system. But let's say that the professor can read. Let's say we don't want the professor to be able to write. They can read and they can, and because in this system, professors can't change who owns the file. Yeah, so they just have, okay, great. So we actually don't need a can own. Let's just say that a professor can read it. That good? That makes sense, intuitive sense? So professors can just read and there's no difference between the two. Now, what permissions does, or what rights does Professor 1 have over Subject 1? Yeah, can kick. So they have the right to kick. What about read or write or own? Yeah, it's unclear, or you could say no, right? Because it's those rights don't mean anything against a student, right? So just because there's a right doesn't mean it actually makes sense against the student. So we'll go with can kick for now. So in this example, if you notice, the rules are that the professors can kick a student from class, but they actually can't change the homework files from what we have now. Okay, P2. So P2 would be similar, right? There's no difference between the professors here. Now, is there anything missing from this? Is there anything let's say, should there be a column here for P1 or P2? Yeah, they're not objects, right? Nothing can act on a professor, which means that we don't need a column for them. So now the nice thing about this model and why this is a very interesting model is because if I asked you the question, can student 1 write to homework file 2, how would you use this this matrix or this table to answer that question?
Just see the intersection.
Yeah, so see the intersection. Yeah, great, thanks. So look up, so homework, subject 1 is the, student 1 is the subject. So we'd look at that row and then we'd look at the homework 2 column and we'd say, nope, homework, student 1 does not have any rights to homework 2. So knowing with this model, we can see exactly what everyone can do on this system. So we can see who can have the, has different rights on this system. And so now and the actions would then change the state of this matrix, right? So if I then said, let's see, we had, so P1 can't change it in our system. So we have this, let's say the next action that gets taken is S1 changes ownership of file H1 to S2. Right? And we can do that because in our current model, we have this rule that that students can change who owns a homework file. Cool. So now, and you can think about this as a state transition, right? So we're actually this matrix is transitioning. So what is different now about this current state? So what does our access control matrix now look like?
So the own, read, and write is going to go down to S2 and S1 won't have any.
Yeah, of what? So yeah, so S2 now on homework 1 will have owns, read, write. Now, we actually haven't specified exactly what happens to S1's access. Does it lose it? Does it not? So we'll say that ownership, you can only have 1. And so let's say it removes it, right? So now S1 has lost rights, and now we can see that S1 doesn't have any access to any of the homework files on the system. Cool. Okay, great. So this is, and now I guess one thing I want you to think about, is there any ambiguity here of who has what's rights to what objects? Yeah, so there should be almost no ambiguity. The ambiguity comes into as the what do these rights mean and what actions change the state. But you could think about if we specified these actions properly, we could specify owns and read and write and can kick in mathematical terms that could use this matrix to think about, okay, if this subject has this right of an object, then they can read the file. Or they can write to the file. Sorry, the actions were creates, owns, kicks. But if I ask you any question, if you have this matrix, you can answer it by saying, does subject 2 have the can kick right to subject 1? And you would use this matrix and say, okay, S2 and S1, nope, doesn't have any rights here. This is just the empty set, which means there's no rights. And that's great. So this can represent, and we can do this for any system. So if you think about any kind of system, we can actually represent it in this way. Let's go then back to our slides. I want to share sound. Okay, let's try that. And then we'll go with, so here's just another example that you can look at it that's more abstract. Okay, so can you see the screen now, the slides? Yay, okay, great. So we can think about even modeling file permissions, and this is where we get into more details of the Unix file system, we can model this in this way. So here, the things that can act on a Unix system is actually not you as a user. So I'll answer a question first in chat. Somebody asked if we change states, we need a new matrix to reflect that. That was just kind of a way to look at the temporal transition of the matrix. You don't have to necessarily create a new matrix, but yes, like that was just a way to visually show how things change. So you don't necessarily need to create a new matrix. Essentially, that matrix would be updated. So the interesting thing about a Unix system is that you may think, so hopefully a lot of you have been into Bandit, you've SSH to Bandit, you've accessed that system. You may think that in that system, you are a subject because you are actually typing in commands. Actually, let's look at this. Let's see. Okay, can you all read this text? Please tell me that's good.
Yep.
Okay, and the size is big enough that you can all see it? Cool. Okay. Let me see if my server's up. Yes, okay. As much as I like typing this in here. Okay. So now I'm on a Linux machine. So we think, when I type in ls, is anything important in there? No. Okay. So when I type in something like ls, right, it seems as if I'm something that's making something on the system. So let's go to /temp. I can make a directory called CSE 365. I can look at the permissions on that directory. I can see that and we'll get into this in a second, I can see that the AtomD user has some permissions. I can change those. Let's just look at changing those, looking at it. Then I can see that I've completely modified and changed those directories. I can create files. And when I say it seems very intuitive that we're thinking about me, the user, but that's actually not what's happening under the hood. If we look at what's actually happening, and I want the tree, there we go. Yeah, so actually we can see that it's not even me. So this is I'm using htop, which is looking at all of the processes that are running on my system. So what's actually happening is there's a process with the process ID of 1406 owned by the root user that is this SSHD process. So this is the SSH daemon that looks for incoming, oh no, I just did that. How did I? Collapse. How do I expand that? Man, maybe the plus sign. Yeah, let's. Oh, there we go. It was the plus sign. Yeah, thank you. I must have done something weird. So we can see that it's the SSH daemon, and the way that processes work in Unix style systems, including Linux and other things. Every process, a process can have children. So that spawned an SSHD process. So this is the thing that listens on port 22, or if you're specifying on Bandit the specific port, it's listening, it authenticates you, and then when you log in, it actually runs your shell, which in my case is ZSH, and you can see I'm actually running htop within there. So every command that I type in, when I'm typing in ls, when I'm typing in all those things, it's actually not me that's doing it. It's another process that's doing it on my behalf. So the point of all this is to say that on a Unix style system, the subject is actually a process. It's not the user itself. And that's important to understanding the model here and how those things work. So does that kind of make sense of this notion of the process is actually doing the thing, not me? Cool. Okay. Then we'll go back. Cool. So we'll imagine a system, and we'll start with a slightly simplified model. So we have two different processes. So we have P and Q are different processes, and yeah. So this is an indirect method. I am asking. So this is the whole point of your shell. When you type in ls, it figures out what program you want to execute, and that process has an action. Your shell process has an action called execute, which actually asks the operating system, "Can you execute this binary for me?" It will try to do that if it can, and it will have rules that uses the access control to understand if you can do it. And we'll have in our system files. So here we're considering files. We'll say a very simple model. We only have two files, F and G, and there are actually a lot of different writes that you can have, including read, write, execute, append, and own files. So we'll think of this as R, W, X, A, and O to kind of simplify things, right? So we have the read, write, the read and write. That's funny. So we have the privileges or rights of reading, writing, executing something, appending something, and owning something. So we can then represent, in this very simplified model, we can represent, let's say, in this simplified model, a system. So we can have processes. So these are subjects, and I can have all the rights on them. Now, the interesting thing that we'll see is a process, especially in Unix, can act on another process. So for instance, I can try to kill I can send a signal to another process. One of those signals is the kill signal, which tries to kill that process. So I can actually interact with other processes on the system. So this is why in the Unix model, the processes are also objects. That's why they have rows. So we can see in this model that P can read and write the file F and also owns the file F, can only read the file G, and can read, write, and execute and owns the process P, and can write to process Q. Now, again, what exactly it means when you can write to a process is dependent on the implementation of the system. Similarly, from this model, process Q can only append to file F. So what's the difference between appending and writing?
Appending is just adding content. Writing could be you can change it, remove stuff, and everything.
Yeah, so specifically, you can't delete things if you only have append access. So if you only have append access to a file, you can only add additional information to the end of the file. Whereas if you have write access, you can completely change any of the contents of a file. Yeah, so that's great. So, for things like, let's say, integrity, especially if you think about how do you ensure the integrity of a log file, you want your logging software to only have append access to a file. And if that's enforced by your operating system, then you can be sure that nobody can overwrite previous log entries. Unless, of course, they're able to compromise your operating system. So yeah, this is an important concept, and that's why I like bringing it up here. Q also can only read and own file G, and P has read access to process P and full access basically to process Q, read, write, execute, and other. So what is it, or sorry, other is own in this example. So what does own maybe mean here? And what does it kind of sort of mean in the...
Can P create Q and delete Q as such?
So let's see, P doesn't have owner over Q, but it does have owner over F, right? So in the kind of Unix model, if you own a file, that means you can change the permissions on that file, and you can specify, you can also change permissions for other people, as we'll see, and you can maybe give other people additional access, and you can also change ownership. So you can give ownership of that file to somebody else. So for instance, P could give Q ownership access over F, and then at that point, Q could be able to change the ownership there. We'll get into more details in a bit. But for now, I want us to think about this as a model. So And specifically, I want you to think about this in terms of you're writing an operating system, right? So the operating system should enforce things like, should be able to enforce things like, should be able to actually enforce these things. So should be able to enforce that you can only read from a file if you have the read access. Okay, so somebody, there's a question in chat about how can you write without being able to read? Yeah, so that's let's say you can open a file for writing, but that would truncate the file so that you can't read what's already in it. So you can overwrite it, but you can't, and you can write new information to it, but you can't actually read what's there. Does that make sense?
Could you explain to us what's truncate in your?
So truncate would be overwrite. So basically, the moment you try to open a file for writing, if you only have write access, it means that it erases all of that file that was there. So you're starting at the first byte of the file, and then you could write more information there. So you know what your process knows what it has written, but it can't read what was already in that file.
Okay, thank you.
And yes, both P and Q are subjects in this model. Subjects and objects, yeah, exactly.
But can't we use the write access as an append access? As in, I cannot see what's written, but I'll just add stuff to it.
Yes, so you definitely, you can. It just depends on what your model actually implements. So we have to look at the details of of what actually happens if you only have write access to a file, what you can do. But it definitely happens. So yeah, but the key difference between append and write access is write access allows you to overwrite what is written, whereas append access does not allow you to overwrite what's already there. You can also, with write access, inject essentially anywhere in the file, whereas append access is only at the end.
So excuse me. So the ownership have like a master control over like read and write, right?
Yeah. So exactly. In the Unix model, the owner of the file can change the access control of that file. Oh, so they can remove all access from the file and then can add access back to that file as long as they're still the owner.
But then can they change like things like if someone writes something and the owner doesn't like it, can they undo the changes? No, like
technically yes. So they could do so. That gets into more technical details about what happens and can two processes like simultaneously be accessing a file. But technically yes, like if you have read and write access, you can be continually reading from that file and then changing whatever that content that you want. So fundamentally you can.
Okay, thank you.
Yeah, so and then an owner can, I don't think they can explicitly, well, at least in the Unix model, every file has to have an owner, but you can change who owns a file. So you could, in this model, P could set Q as the owner, and now they lose ownership, so they can no longer change permissions, but Q is the one that can now change permissions. Okay, and then, yeah, there's always exactly one owner per file. Yes, and that is, actually, if we go back, that's this first part here when we do ls-la. So this tells me that this current directory, which is CSE 365, is owned by Adam D, but the parent directory ... is owned by root. And we'll get into exactly what all these things mean. We don't need to do that here. We're just kind of going over a very simplified model. So I want you to think about this model now. So with this, as we said, we know every subject and every object, what rights they have on the system. And from the idea of you are writing now the operating system that has to implement this access control, what's the benefit of having everything in this matrix? So somebody wrote in chat readability, right? Or maybe comprehensiveness or no ambiguity, right? Another thing for performance that's great is constant lookup. So if everything we're using hash tables, we could look up if we say, okay, P wants to access G, let me look up in my hash table, look up P, and then look up G, and I can know exactly in constant time what access it has. It can be easy to query, like we said. That's great. Yeah. So then before we get to the next part, let's think about what happens if P creates a new file. How does this matrix change? Yeah, a column is added, right? So we'll add another column to this table. And then what happens if I create another file? Same thing, right? More columns. So every time we create a file, we're adding an additional column to this. And in order to be secure, we have to specify what every subject has with that new file, right? So think about a modern, operating system. How big does this matrix have to be to capture all this information? Yeah, very big, right? Millions at least. And let's go back here. Okay, so I have roughly 164 different processes running on this system. How can I? Let's see, this may tell me roughly how many files are on my system. So I would need, just right now, the operating system would have to store a table of, let's say, 164 rows, which is and it's not number of users, it's the number of processes, at least. Let's think of that model right now. So I'd have 176. Let's see if this is ever going to finish. I actually don't know how big this server is. But let's let that run. And we'll go back to it. So would that be then a drawback of this system? Yeah, if we think about memory or storage, right? We have to store this matrix model somewhere. And if we're letting people have access to this and they can create as many subjects as they want, they can spin up different processes. So I could spin up 1,000 processes, and each of them, if I have 1 million files, that's now 1,000 times 1 million new pieces of information that I have to store in my operating system. And so this is a great model in terms of how to think about access control. And you can see at a glance exactly the state of everything on the system. So you can ensure that everything is exactly how you want it. Unfortunately, it basically becomes it's untenable to actually implement in this way. So we talked about, benefits, the drawbacks that we just talked about. And so the real thing is, and when getting to this, so it's not a problem with the model per se, but it's a problem of the implementation. And this is kind of a really interesting case I like to bring up of, you can have this beautiful theoretical model of something, but now when you actually implement it, you go, oh, wait, that model doesn't actually fit reality. How do I even have enough bytes in my memory to keep track of all that information? And if I have, let's say, a massive system that, eventually I think we'll create a server that there'll be roughly 600 user accounts for all the people in this class. That's going to be a big system that we want to make sure that we need to keep. There we go. So this file has 2 million. This system has 2 million files. So for every process, for every row, I'd need 2 million additional cells, right? Because there's 2 million columns in this table. And you can see how that could quickly get out of hand. So now the question becomes, okay, then what do we do, right? Because, we don't want to just give things up, just give up on this model. we still want the benefit of that. Hey, we want all of this access control information. This is important information. So one of the ways, so one thing we can do is we can try to maybe group things together. Let's say we can, rather than having each process as its own row, maybe we abstract them to users. So a process belongs to a user group. And then that way that can simplify things. We'll still need, all for every user group. And when I add a user group, I need to add a bunch of files. I need to also will have to, for all the users in the system, every time I add a new file, I'll have to add a new row, which is going to add up to a lot of different things. And so basically the way to think about this is what if we, rather than, and one of the key problems is here we have everything in one giant table that's trying to capture a ton of information here. But what if we split this matrix up into different slices? What if we actually looked at each column and just stored each column? So this is the notion of, if you've heard this term before, it comes up a lot, of an access control list. So basically think about, okay, rather than think about this giant matrix, let's think about for every file, what processes, what rights do the subjects have? And we can actually have a nice little implementation benefit here. We can say, if you're not in the access control list, what access do you have? What would be the most secure option? None. Yeah, so if you're not in this list, it's like a bouncer at a club or something, right? Looks at the list, be like, sorry, you're not on the list. You don't get in, right? So this way, we only have to store from the column those subjects that actually have a right to our file. And you can think about it, if a very big system where rights aren't being shared so much, this actually can cut down a lot. So in this case, we'd split it up so that so for file F, we'd say that P has read, write, and own, and Q has append, whereas G has process P has read access and process Q has read and own access. So what's the benefit here in comparison to the previous big matrix model? Yeah, so it's simplified a little bit. It's condensed. It's also, think about what happens when I add a new file. Or what happens if I add two files at the exact same time? Before, if I had this big matrix, what would happen if I added two files at the exact same time by two different users? I need to make sure that I made the changes to that giant matrix one at a time, that I couldn't do them at the exact same time, because otherwise they step over each other, right? I want to make sure that only one change is being made to that matrix at the same time. Now, if each of these are stored separately, let's say, and where would I store these? Let's think now again about a little bit about implementation. So then how would I implement something like this? Where would I store this information? Should I just add it to the start of the file? So every file has information at the start of the file that says which process has access? Right? So why can't it be part of the file itself? Like, let's say it's just literally this text, P:/ RW0, new line, Q:/ A, new line, and then content of the file. Yeah, so the key problem there is now anybody that can write to the file can change the permissions, which is not what I want in my model. Who in my model should be able to change the permissions on the file? Owner, only the owner, right? So if we say, okay, then who has to store this? Well, fundamentally, the operating system must have to store this information somewhere. So eventually what happens is this becomes metadata on the file system about who can have what access. So fundamentally, it needs to be stored somewhere where the operating system can ensure that a user, another process can't just edit these attributes, because if they can, then that just becomes a massive problem. Cool. So yeah, so this gives us some clear benefits, right? We can delete, we can, when we create a new file, all we do is add that new metadata right directly to the file. We can do that, simultaneously as many things as possible, because that doesn't affect anything else. Are there any downsides to this approach? Oh, metadata just means data about data. So it is information about data. So file metadata would be information about a file. So in this case, it would be what rights do the subjects in the system have on that specific file. So what's a downside of this approach? Are there any? Should we just use this always? So one thing we'd need to, so we need to worry about thread safety, things happening simultaneously on a specific file. That's definitely something you could think about. You just can't get rid of that whole thing. That would be if you have two different things accessing or trying to change the metadata here. Let's think about the example of the students, right? The professor had the ability to kick a student out of the class. And what would then happen if I kicked a student out of the class? In our system, not in general. Yeah, they'd lose their permissions. Great, thanks in the chat. So they would actually lose their permissions. But how does somebody actually lose their permissions? So think about in the matrix model. What would I do in the matrix model here? I need to either delete this, or I need to make sure that every cell in this row P is empty, right? And maybe then can I delete that? Excellent. Now, in this case, what would I need to do in order to, let's say, revoke all of P's access? Yeah, great. I have to go through every single file, right? I'd have to go through every file, delete this row P to make sure that P has no access. And I actually lost the ability now to have all of the access control information stored in one place, right? So if I wanted to know who has access to what on the system, I now have to look at every single file on the system to understand what everybody has access to. But if I only care about specific files, like if F is a super important file, all I have to do is look at this access control list of F, and I can convince myself that if it's secure or not. Well, maybe. Right? So yeah, the important thing is there's no perfect solution here. It's all trade-offs, right? But fundamentally, with this model, I can still represent everything I can represent in the matrix model, because I've just taken the matrix and I've just cut off every column. But fundamentally, I can still store everything here. Does that make sense? So does that, if you have, let me know, I'll pause for a little bit if you have questions on the trade-offs between like the access control list versus the matrix model. Cool. All right. And of course, so if we thought before, hey, let's split up this matrix model by cutting up the columns, what would be the other idea to try there? Use the rows, right? Exactly. So if we said, hey, what if we did the columns? What if we just did the rows? So this is actually called capability lists. So different from an access control list. And you can think about the difference here. An access control list is about an object. So it says who has what access to this object, Whereas if you think about it from the row, a row is a subject. So it says, what can this subject do on this system? So that's a capability. So basically, we now store each row of the access model with the specific subject. So P would have some metadata again associated with it. Again, we'd want to, by the same logic, securely store that in the operating system that says, okay, process P has file F has read, write, and own, and file G has read access, and Q has for file F append access, and for file G read and own access. What about other files that aren't in this access on this capability list? No access, right? Same principle as before. We default to have no access, and that way we can make sure that things are secure. So what are some of the benefits now here? Yeah, so deleting a user's permission is super easy. All I have to do is delete this capability list, right? So removing subjects is incredibly easy. And I can also audit a user very easily. I can say, okay, the subject, what access do they have? And I can see exactly all the access that each user has, right? But again, now a problem is, what if I want to say who has access to file F? Or, yeah, great example, Austin. If I remove a file, or let's say add a new file, I have to then go and update all the capability lists of everybody in my system. So you can see that these have a very natural trade-off depending on if you're focused on subjects or you're focused on objects. Another cool thing here that I'll briefly mention is that one of the cool things about capability lists is you can rely on cryptography here a little bit, so that the operating system itself doesn't have to store the capabilities. It can create this capability list, cryptographically sign it in such a way that whenever P wants to access a file F, P asks the operating system, hey, I'd like to access file F, and it goes, great, show me your capabilities. It shows it, it's encrypted blob. The operating system can check that and verify that, yes, it indeed has access. One of the tricky things is this now allows delegation. So F could possibly delegate to file F to somebody else by giving them this encrypted token, but that's kind of for later. So yeah, so there's no perfect system, but in each of these systems, we can represent everything that the matrix can represent, right? Any possible access control system. But we just do that in different ways that have different implementation trade-offs. So access control lists vertically, capability lists horizontally. Yeah, then we can think of maybe another way of, and this is more, we can think of a subject, the access, and the object. So we can actually just split it up like this. So we can think about a three tuple, so like a list with always 3 elements: the subject, the access, and the object. And so this would be kind of another way of thinking about this, but it's definitely not as common as access control lists and capability lists. So yeah, okay, so we talked about this. So this is, again, where we've talked about a little bit about authentication. So authentication is, who are you? So with an access control list, we require that we know exactly who the subjects are. So encryption is basically about integrity, so that we know that somebody hasn't modified the capability list. Yeah, so it's about ensuring integrity there. Whereas with capability lists, so as long as somebody can present us the proper capabilities, we actually don't care who they are. So we actually don't require authentication, which is kind of an interesting thing. But of course, we have these problems that we can't, we don't want capabilities to be able to be forged. So we don't want anybody to do that. That's why we'll eventually get into encryption here. So the UNIX, modern Linux systems use both, believe it or not. Well, use a combination of complicated things. Windows itself uses both. So Windows uses a bunch of different things. We'll get into the exact way of how the main way that people are used to it is a Linux machine will use and a Unix machine will use access control list. So propagation is for a capability. Can a process give their capabilities to another process? So that would be propagation. Can those capabilities propagate without the control of the system? Yeah, excellent. So yeah, basically, this is kind of just another way of thinking about it. So we have some directory with some files, right? Access control lists break up the access rights based on the file, whereas capability lists are thinking about subjects. So the user, a specific user has different rights on that file. Oh, fila B. But we already talked about that. Cool. So yeah, so one of the kind of another interesting thing here is this concept of least privilege, which we've mentioned before. So least privilege is the idea you should only have access to the things that you need to do your job and nothing more. So because capability lists focus more on the subjects, we can ensure that the access that they have is limited to just what they need to do their jobs. So for instance, thinking about a logging service, which I mentioned before, it'd be very easy to see that a logging service that has the capability of only appending to a certain file, that would be an easy way to verify that it has least privilege and that the logging process can't go haywire and do anything. But again, this is kind of we're getting more very fine-grained separation here because fundamentally you can represent anything in any form, but as we saw, they kind of have inherent trade-offs and drawbacks. Other thing is we talked about even access review. So if we have an access control list, it's super easy to say for this file who has access. Whereas for capabilities, it's easier to say what does this subject have access to, right? We talked about that. We talked about revocation. So this was the notion of kicking somebody from class. So how can I revoke all their access? So if we have an access control list, if we want to say, okay, I want nobody to have access to this file, well, it's pretty easy. We just delete the access control list and now nobody can have access to that file. Whereas capability lists are better for revoking a subject. So if I want to optimize my system around kicking students out of class, then capability lists are going to be better for that because I can just remove their capabilities. Cool. Okay, yeah. So this is kind of about the propagation aspect. So what we talked about is we need some way to actually give capabilities. So we need the operating system support, which we need in an access control list. If I want to say, okay, I want to change ownership of this file, the operating system needs to update that. Information. Whereas in a capability list, I have to somehow figure out a way. There we go. So yeah. Yeah, so if I may need, anyways, I think this is fine. We don't have to go into details on this. Now we get to the Unix access control model, so we can actually see how this works. Okay, so the normal thing. So now we need to then put on our implementation hat. So with an access control model, with our access control model, yeah. Actually, we'll go back here. And let's go fun times back to our model. Okay, so access control lists, right? So we have our access control lists. Now, you're implementing this. You want to store extra data for each file, right? So for file F, you're going to store extra data. How much data do you need to store? How much space do you need to store the access control list? Yeah, you need space proportional. It's dynamic, right? It depends on how many subjects and how much subjects have access, right? So we don't have to store access to, we don't have to store information for subjects that have no access, but let's say your system by default has read access to all files. So therefore I need to be able to expand to an infinite number of subjects. Now, this is clearly a major limiting problem, especially if you think of Linux was created and Unix systems were created back in the day where there wasn't unlimited space on file systems. So in order to get around that, they've actually have simplified this model in such a way that it reduces the amount of information that they have to store. So fundamentally, it actually uses only 12 bits per file. And it's logically grouped into 4 sets of 3 bits. So the, and this is when you type in ls-la, you'll see something that kind of looks like this. We'll get into it a little bit. I will, okay. Yeah, I want to show an example. Okay. Because I think it's much better to learn through examples. Okay. Okay, so when I type in ls-la, I don't actually see 12 outputs. I see 1, 2, 3, 4, 5, 6, 7, 8, 9. So I see 9 bits. We'll see that it actually has at least the 12 bits of information, if not more. One interesting thing, so the first one is D, so if it's a directory or not. So if I create a new file called testing, I'll see that the testing file, which has 0 bytes. So just walk through this. So this first bit is, if it's a directory or regular file and probably other information as well. Then the next 3 bits are important, the access control bits that we talked about. This, I actually don't know what this is. That's interesting. The next one is the number, who is the user that owns the file. The second one is who's the group that owns the file, then the size, and then the last date that it was changed, and then the name. So the important concept in Unix is permissions are organized around what permission does the owner of the file have, what permissions does the group of the file have, and what permissions does anyone else have on the system that is not in there. So that's why you have this AtomD and AtomD. And if you run the ID command, it will tell you, okay, your user ID is user ID 1000, which is the name, text name AtomD. And your group ID is 1000, which is the text name AtomD. And I'm a member of all of these groups on my system. And this allows you to do things like only members of your group have access to a certain file, et cetera. So for instance, well, anyways, we won't get into Docker. So the way these permissions work is, so this file testing is read, write, no execute, read, write, no execute, and read. So this means that the user of this file can read it. Read on a file is very simple. It literally just means read. Write means write, just like we talked about. The next bit is execute. So can we execute this file? So this is why if I do /testing, it will say permission denied. So it's telling me permission denied because I don't have permissions to execute this file. It's not failing because it's an empty file. It's failing because I don't have the permission to execute this file. The number is so Nathan, thank you, put in the chat, the number is the link count, the number of places the file or directory is used. Okay, so that has to do with like hard links and stuff like that. So we actually already went over this. If I wanted to make this executable for me, just the owner, I can use chmod, and there's 2 different types of syntax. So when I did like 777 testing, this is literally me setting. So this is octal in those bits. So this is octal. So 777 is 9 all ones, right? In terms of binary. So this means that in this example, all of these bits will be 1. So this means that let's look at ls-la testing. And we'll look at this and we can see that it is now readable, writable, executable by the owner, readable, writable, executable by the group, and readable, writable, executable by anyone else. And now if I try executing this, That is shocking. And it doesn't even give an error. Fascinating. Okay. I have absolutely no idea why this actually executes, even though it's literally an empty file. Let's. There we go. Okay. That's, yeah, that definitely shouldn't work. So 777 is octal again. This is octal to set the bits. I can also, and I kind of have done this enough. So this would be 666 would be non-executable. Is that right? Yeah, so it's just readable, writable. 664 was the original. So that's readable, writable, not executable, readable, writable, not executable, and just readable. So if I tried executing that, it will of course tell me permission denied because I cannot edit it. So, or because I cannot execute it. Great. You can also do something else with chmod. You can say, okay, I want the owner. So the owner, I want to add plus the execute permissions. Now, if I look at it, I should see, oh, of course, I messed that up. I messed that up because O actually stands for other, not owner. I think I always mess that up. So I can do that again by O minus X, so to subtract that. What is actually owner? A U is for user. Thank you very much. Okay, great. So I can just change this bit by saying I want the user to be executable. And now I can execute it. And now it'll let me execute it, but of course it will fail. Do y'all want to see me being another user too? Let's do that. Okay. So now I'm running basically screen to have two screens. I'll be root in the other one. Okay, of course that will not work. Okay, so now I've changed myself to the nobody user. So I am nobody. And I'm in this directory. And if I execute testing, it'll say permission denied. So why is it saying permission denied? Yeah, the other group doesn't have permission, right? So I can't execute this. Can I read this file? So let's cat testing. Yeah, so I can read the file. Now if I go over here, back as my user, and I do chmod other minus R testing, I'll see that hopefully nobody can read that file. So then I should see permission denied. Let's see, can I change permissions as the nobody user? So it says operations not permitted because I can't do that, right? Cool. And so I can even remove, let's see, I always love just typing in random commands that people suggest. So what happens if I get rid of all permissions, right? We can see that there's no permissions here. So now I, even as the owner, can't execute it. Can I cat read that file? Nope. And right, so I can't, even the owner of that file can't do that, but I can give myself access again. So 600 is read write. So now I can read the file. Of course, there is usually there's always some kind of, so now I'm the root user. So I'm the administrator of this system. And the administrator of the system is allowed to do anything. So I can read this file. There's actually ways that you can reduce the capabilities of root so that root can't do everything. But in this case, I can read So see, yeah, because I don't own this, I can't do it, but let's see. Yeah, so root can change the files. They can also change the owner. Yeah, let's see. I can change the owner. So the syntax here is, okay. So the syntax here is chown nobody. And so now, oh, nobody. That's strange. I don't know why I can't do that. Root definitely should be able to. Yeah. Must be something about changing ownerships or something. Yeah, I'd have to dig into this to figure out exactly why that's not happening the way I thought it would, but now the tables have turned. So even though that user created that file, we can't actually do it, but now nobody can. And now let's put it back. MD. Okay. Cool. There's some other special bits. So we said there's 12 bits. We've only looked at the 3 bits. We've looked at read, write, execute for the file's owner, for the user, read, write, execute for the group, and read, write, execute for all users, so everyone else on the system. But there's actually 3 other important bits. So, and again, the question is, how does it actually know who I am, right? Again, it doesn't know that it's me. It's not looking through facial recognition to look at Adam D. What it's doing is, yeah, okay, great. Bash root. Yeah, so what it's doing is looking, the operating system stores for every process on the system, who's the owner, who is the, what user ID is that associated with. So the bash where I'm running is user ID nobody, group nobody. The Adam D one is Adam D, and the root one is owned by root, and that's what it's using to detect those things. Okay, very briefly, these other file permissions are actually important. So again, when I want to, let's say cat etc. So the etc password file is actually a super important file on the system. It has all of the user accounts. So it has the user account. It used to have the password go in the second field. It has your user IDs and your username, any comment, your home directory, and your shell. So if a user could edit this, if you could edit this file, etc password, then you could update your user ID to be 0, which would mean you're the root user. You could change the password for other people and change their password. You could basically do anything, but we can see that its etc password file is only readable. It's owned by root, group root, and only root can write to this file. So this, please don't work. Yeah, so I can't write to that file as a user. But if I go do CSH, which is change cell, oh, I don't even know my password on the system. Maybe it's that. Nope. Ah, there we go. Okay. So let's say I want to change my password to bin.sh. I do that. And then cat etc password. I look at the user Adam D. Suddenly, this seems like I violated all the rules that we talked about. I just changed a bin/s. I just changed this etc password file. But only root can change this file, right? Have I just severely hacked this system? Am I the owner of this system? And I know we're at time, but I'm gonna keep going because I want to finish this out real quick. So how does that happen? So let's look. The command I ran was CSH. If you ever want to know exactly where a thing is located, do which, and then that command, it'll tell you the path to the binary. So I can see ls-la user bin CSH. And now I see something we haven't seen before. I see that it's a regular file. It's readable, writable, and a lowercase s here instead of an x. Readable, no writable, executable, readable, no writable, executable, owned by root. What this means, this S is the setuid bit. So this is one of the first bits in there. And this says that this CHSH program runs as root. So that's what setuid bit, which means it runs with the permissions of root. So when I run this again, watch, we can look. If I do psaux grep chsh, we can see that the CSH program is running as root. And if I run htop, and let's look at the tree view. I said, let's look at the tree view. Oh, thank you. Fun. Okay. If I look at CSH, so CSH is running, which is a child of ZSH, which I ran. But ZSH was an AtomD process, and CHH is a root process, as we saw. So we can see CHH is a root process. So this is how the operating system allows you to do things like be able to edit a file that's only editable by root. It's a C program that is compiled that when the setuid bit is set, it sets that user that owns that process as root. And this is how, as a user, you're able to change important files to be able to do things like that. Set GID is to set the group ID, which is similar, except instead of setting the user of the process, it sets the group of whoever is the group of the process. You'll actually see that, I believe, in one of the binary hacking homework assignments. And finally, the sticky bit is, it's not really relevant anymore. It comes from well, it is relevant in the fact that if you look, so this T here in temp is the sticky bit, and I believe it means that, let's see, do I have it there? Blah, blah, blah. That's yeah, okay. Sticky bit on a directory means that people can create files in the directory, but cannot write or rename other directories. We also didn't go over what readable, writable, and executable means for directories. They're a little bit more complicated, but when we come back, so this is the mechanics of how it works. I want you to be thinking about, from now until then, how does this relate to the matrix model? And what are the difference between the actual implementation of the UNIX access control model that we talked about here? How does that differ from the matrix model? So thanks for bearing with me. I know I went over a little bit. I know we had some silly Zoom sharing problems.